Okay, so we have now next problem, 244, C5H10, similar to previous one, except now we have two oxygen. So now let's look at the index. So first thing is we've calculated the index and hydrogen deficiency index. So again, we have 5 times 2 plus 2, that's 12, minus, we have 10 already hydrogen divided by 2. So again, it's only 1, so we have 1 double bond. So there's a good chance that would be C double bond O, like previous example, but we have an additional O. So that should help us find what the structure is. We have a double bond, and we have an additional O. So these are, as we know, influence the ppm, and also don't have any hydrogen to contribute to the spectra. So the spectra doesn't show any oxygen. We have to remember. So let's go look at the signals. We always say we like to number them, and I have a habit of numbering from the right to left, and I always forget which way to go. So if I call this A, B, C, and a D, identify the number of different signals. Then number 3, it says use area. So we need to look at the area like we did before and see if that area help us to identify the number of hydrogen or protons for each of those signals. The first one, the area is 33.2, 48.4, 33.3, 48.7. So these two are the same, very similar. So I use 33.2 as my lowest number. So if I take 33.2 divided by 33.2, that's 1, of course. Then we have 48.4 divided by 33.2. So that's about 1.3. Then we have 33.3 divided by 33.2. So that's 1 basically. Then we have 48.7 for the A. So 48.7 divided by 33.2. So that's 1.46. So again, they don't add up. They don't add up to 10. So if you multiply it and make it integers, because you can't have fraction of a proton. So if I multiply all these by 2, so I would have 2 hydrogen here, 1.3 by 2, let's say. So this would be 3. 1.25, yeah, 3. Then we have 2, and we have 3. So these are hydrogens, right? So I'm going to write it for my A, B, C, and D. So we have 3 hydrogen here, 2 hydrogen here, 3 hydrogen here, and 2 hydrogen here. Signals, if you look at the signals, we have a triplet here, we have a triplet here. Again, like before, a sexlet here, 6. So we have 6, right? A single and a triplet here. Got a little bit busy, but it helps us to identify it and put the puzzle together. So for A we have a 3 hydrogen, We have 3 hydrogen and it's a triplet. So we have 3 hydrogen and it's a triplet. So if I put the 3 hydrogen here, so now we realize if I have these 3 hydrogen and they're a triplet, there should be a 2 protons and 2 hydrogen next to it. So I put H here and H here. So that's the fragments that dealing with A. So dealing with A, we have a 3 hydrogen next to 2 hydrogen. And the ppm is about 0.9. It's about 0.9 ppm. So let's look at the B. So this was A. B we have, like before, we have 6. So it really has 5 protons next to it, like previous example. And it's made of 2 hydrogen. So I put the 2 hydrogen here. And then on the left side and the right side, I add up 5 protons for it. It really doesn't matter where I put it. I'll put it 3 here, 3 a methyl group here, and 2 H's here. So these 2 hydrogen, which is about 2 point, what is it now? 1.6, about 1.7, 1.6 ppm is in 6 signal. So the 3 plus 2, 5 plus 1 is 6. So that was my, so this is my A, this is my B. So let's go look at the C. C is a single one. So it makes it basically easy. So there's nothing next to it. So this would be a little bit challenge. So we can have, so I'll draw it something. So we have 3 hydrogen. Now I write on the right side O. Remember we have a O. Or it could be H, 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 C double bond O. And we're going to find out it makes a difference because the O and the CO influence on the next proton and this methyl group. So if you look at the methyl group has this CH3 and it's around 2 ppm, right? Around 2 ppm. Remember, methyl group is 0.9. If it was next to an oxygen, you would have add like 3 or close to 3 ppm to it. So this would have been 3.9. Now, if there was 0.9 plus 1, 1.9, and this, look at this, is 1 point, close to 2, 1.9. So we can say that just by the ppm and knowing the change in ppm, the C double bond CH3O probably is not the representative of this signal here. Most likely would be C double bond O based on the ppm. Based on the ppm, we learn. So we did A, we did B, we figure out what the C should be. We have a good guess for that. Now we're going to look at the D. So D again is 2 hydrogen. So D is 2 hydrogen, but it's split in 3, so it's triplet, right? So if you have 2 hydrogen, So we have 2 hydrogen, and next to it we have 3 hydrogen, or 2 hydrogen, I'm sorry. We have, so it's a triplet, right? So it's a triplet, and it's very downfield. It's 4. So it's 4, right? So it's next to it would be 2 hydrogen, and it's going to split in 3, a triplet. So this is my D, and look at the ppm. The ppm is 4, so it's really downfield. So it's going to help us to figure out what the structure is, because this really means that it is close next to the oxygen, because it's very low. Remember, we had 1.2 and we add 3 to it, so we had 1.2 for the typical CH2. So if I have 1.2, add 3 ppm for an oxygen, so this would be 4.2. So most likely this has oxygen next to it. So D probably has a CH2 next to the oxygen. So we sort of have our little challenge here. So now we're going to put them together. Usually the easiest thing to start is the one that doesn't have any split, or at least that's the way I think. So the one that we're looking at is C. So C doesn't have any split, is a singlet. This is the C, right? So let's draw that and see what we can get. So if I draw a CH3, CH3, CH3. So this would be my, we call it C, right? So this is my C. Then next to it, we decided is not an O, it's a C double bond O. So put the C double bond O. Now we can play with it, but most likely if you have two O's, this is an ester group. So this is an ester group. So an ester group means that I have to put the oxygen here. And of course, next to it, I have basically how many carbons did I use so far? I only use 2 carbons, right? I have 5 carbons. I have 3 carbons left. So those are most likely 2 CH2 and 1 CH3. So I put a CH2 here. So this CH2 is now next to an O because it's very downfield. So that's really D. So that's really D. So this is the CH2 is representing by D. And D, if you look at the structure, is a triplet. So it has to be next to a CH2. And then this CH2, we use 1, 2, 3. So let's say we have to use 1, 2, 3, 4. One more carbon. 1, 2, 3, 4. So that has to be CH3. So now we can tell this CH2 here, we have 3 and 2, 5, plus 1 is 6. So that's the one 6, B. So this is B. Then we have the last CH3, which is next to the CH2. So that's a triplet. That's a triplet. So that should be A. Yeah, look at that. So that's the structure for this ester and its corresponding NMR. So this is CH3, CO, O, CH2, CH2, CH3. Then we're going to go backward in a second to look at going from the structure to figure out if we can make this a spectral or not. Thank you.